Okay, I think we're good. I feel like I'm missing something, but I don't know why. Okay, give me. Right, so the thing I wanted to mention is that I feel like last class might have been a little bit confusing. So to try to sort of help with this, I've decided to present things in a slightly different way, and hopefully this clears things up, because I think that, yeah, the things I said last time in the order I said them could have made things a little more confusing than they maybe should have been. So like, I still have all the stuff as before, but in a slightly different order, maybe. Anyways, well, hopefully this helps and doesn't make things worse, but we find out today. Okay, and I want to just take one step back and go back to where we ended with the optimization stuff. Okay, so just before we talked about this evaluation things and these different like true expected loss stuff and whatever, just forget about all that for about a minute here. And just remember what we were doing in optimization. In optimization, our goal was to minimize the estimate of our loss function. And we talked about, we kind of ended on this polynomial regression business where we increased the function class, which allows us to have better predictors to pick from. And then we said we could make this L hat smaller and smaller. And like visually, the way you can think about the predictor you output is as follows, where as you increase P, you get something that fits data points better and better. And these are the data points in your like data set, right? And I wanted to just make this one other point a little bit more explicit, because this is going to be a plot that's going to be very important, which is I said something like the loss for f hat 1, which is the best predictor that's a degree 1 polynomial, will always be at least as large as the estimated loss of f hat 2, right, which is the best predictor that are of degree 2 polynomials, and so on. So of course, if you increase the degree of your polynomial, right, the best predictor you can get out of the set is always going to get better and better, which means that the estimated loss is smaller, right, these inequalities. And eventually, if you make P really, really large, you can get to something like 0. And I want to exaggerate this plot because we're going to see this plot a lot, and it's probably helpful to start at the very beginning, which is you get something like this, which is if you plot the estimated loss of your predictor as P increases. This means the function class is getting bigger and bigger. It includes more things. What you end up finding is that your estimated loss keeps going closer, like getting smaller and smaller, and it gets closer and closer to 0. Okay, so that was the story. And then we asked, okay, like, aren't we done at this point? Like, we wanted to minimize this estimated loss. If we just make P larger and larger, then we achieve this. So like, why not make P as large as possible? And the intuition was that if we try to make P larger, and like what might happen is we do this thing called like we kind of overfit the data, which is we fit to the data set really, really well, but maybe on new data points, which was our goal, and I'm going to rephrase this more precise in a second. Our goal is to like predict things well on new data points. And what you might see is that, okay, like if you end up with a predictor like this, maybe on new data points, you're not going to be as good as you thought. And mathematically, the way we like this, like what was the, like kind of the term that told us how well we do on new data points? Well, that was this expected loss, right? So this is the thing we really cared about, which is like the expected loss of this predictor we output. And so really, this is the question we're kind of after, the thing we're really interested in, which is what does the actual expected loss of our predictor look like, right? This is the estimated loss. What does the actual thing look like? And this thing you should always think of as how well do I do on new data points? Like if I were to see new data, which is my goal, right, to predict new data, the like actual labels from new features, how well would I do? And if you go back to the supervised learning part, we really spent a lot of time arguing that this was a good objective, like a good representation of that. Okay, and so yeah, like the question is, what does that thing look like? And like yeah, like does it look really like maybe it follows the same trend as this? And so like if you increase P, then maybe this is actually L of f hat P. If this was the case, then we'd be like in business, right? We just keep increasing P and our true expected loss goes down. But what we're going to find is it's not quite so nice. Okay. So that's really the preface you should have going into this evaluation business. Is like we're trying to compare this to this guy, and we're trying to understand what is their relationship. Okay. Now we discuss the relationship. And the way I do this is I first remind you, like, everything I just kind of said, which is our objective is to make the expected loss small for the predictor we output, right? This is our learner, it outputs a predictor. And there's just one more caveat, which is like, like if you only ever worked with one fixed data set and no one ever, it's always one fixed data set, then you wouldn't need this expectation outside. But the thing is, like, yes, you do work with a fixed data set, but you have no idea what it's going to be. Like, you never really know what you're going to get. So what you want to do is you want to be basically good on any possible data set you can get. And the way we kind of capture this is just with this extra expectation outside. And it's like a kind of a technical detail, but it should make sense. Like, of course, you're going to really only work with one data set, but like you have no idea what it's going to be. So what you want is to be good across all the different data sets you could really get. Okay, so that's all that this expectation is saying. But at the end, you really want to just minimize this true expected loss of the predictor. Okay, and we had this algorithm to do this, right, which was empirical risk minimization. This was just the definition of our learner. And we had multiple ways to implement this using like closed form solutions and so on. Okay. And this thing had two steps, right? We're trying to minimize L of F. Trying to find the F that minimizes this. But we said we don't know what L of F is, this expected loss. So what we do is we just have an estimate of it, and then we minimize that estimate. And all these algorithms and stuff we like spent time basically trying to like talk about. It was in the optimization part, and it was all about minimizing L hat. But like, okay, so that was our learner. That was like basically what almost all of machine learning stuff is based off of, is different versions of like optimizing this L hat thing. But a natural question arises, which is like, when should we expect this like ERM learner to be good? Okay. And yeah, like there's really two things that affect it. And it's very clear if you look at here. So the first one is just like, how good was this estimate, right, of our predictor, this thing relative to L? We already discussed this thing, and this is going to be very important. And the other thing is that we said that we are not optimizing over all predictors, but we're optimizing over some function class, which is we constrain ourselves to some subset of functions. And I said that this is like an important thing because for computational reasons, you can't really search over all functions. But we're going to see that in terms of like estimation quality, it's also going to be important today. So here are the two type of things, which is like ERM, we can expect it to be good, basically when this function class really does contain a function that makes the true expected loss small, right? That should be intuitive. And the other thing is that you can also expect it to be good when the estimated loss of the function, like the predictor you output, f hat, is actually a good estimate of the true thing, because then you know that this thing that we optimized actually is truly representing the thing we want small, and the thing the function class we were searching over indeed did have a predictor that could make it small. Okay. And so we're going to talk about this in a couple pages, and we got to it kind of last time, but I really want to emphasize this part here, which is, said it many times now, like how close is our estimated loss to the true expected loss. And maybe I think this I didn't really do a great job of last time, so I remind you. And the way to look at this is the following. So like, yes, this is the question, how good is this guy compared to this guy? So I gave this example last time, which is like, okay, the high level story is the problem that arises is the fact that we pick our predictor based on the data, okay? And then becomes this dependence that like, you're depending on the data, so then you have some problems, okay? So, but the way you can think about the story is, first of all, imagine you picked a predictor that was not based on the data. And the way you would think about this is you pick a predictor first, and then you gather data. And in this scenario, this is like the classic statistics scenario. Here, everything works out really nicely because your predictor was in no way influenced by the data. It's like you have a predictor, and then you just want to see how good is it or something. So you gather data, and you see how accurately did it fit the data. But the problems arise, okay. And there, when you have this process, what happens is that really the expected value of your estimated loss is the true expected loss, and the variance goes down as 1/n. This is all I wanted to communicate last time. Forget about like writing out the details of this. Like, things work out nicely when you do this type of thing. But the problem arises in our situation because we're gathering data first, and then we're picking the predictor based on the data. And the story looks like this. You gather the data, And then you pick your predictor. And this is this red line. And the predictor just fits the data like you really make it this like contorted shape to fit the data really, really well. And then you're like, okay, like, is this a good estimate on new data? Well, like clearly it's going to have some problems at the very least, because like if you get any new data, right? Let's imagine these purple points. You can see that, okay, what you're going to find here is something like that the L hat, your estimated loss of this F hat guy, right? Well, it's going to be like approximately 0. You fit the data almost perfectly. But you can see in reality, like the true L of this F hat guy is like it's definitely greater than 0. And maybe I put it here, like, really this guy is greater than this guy. Okay, like, you can see if you get new data, you're not like fitting it as well as you thought. Okay, so, and this is the high level problem, which is that if you pick your predictor based on data, you don't have these really nice kind of statistical guarantees you would have. And so in particular, you no longer have that this like L hat guy is now actually L, so the estimated thing. And we have this extra expectation just out here, because now this F hat really is like, it changes as the data set changes as well. And so there's this extra expectation you need to take over the data set as well. Okay. But yeah. So this is the main point of the story, is that estimated loss of our predictor is not going to be equal to the actual expected loss of the predictor. And then I tried to write out some math stuff, but I really like you don't need to really know the math. All you need to know for this is this main point, because this will get you the whole way through, which is, okay, so the problem here was that these loss estimates like are no longer independent and identically distributed, which meant that F hat of D now depends on each one of the data points. And this caused this problem we talked about above, but really the problem that comes, and you can show this, is that if you try to look at how far away these things are, right? So I said they're not equal, but the question is like, how far apart are they? And like what affects how close they are and how far apart they are? And this is the two most important things probably to remember from this whole thing, which is if you compare this expected loss and the estimated loss of our predictor, you will find that this difference changes with the function class you pick and the number of data points. Okay, and it scales and it changes in this like specific way, which is that if you make the function class more complex, the estimated loss is going to be a worse estimate of the true expected loss. Okay, so make the function class bigger, this estimate gets worse. However, if you increase the data, then this estimate gets better. Okay, and now I show you a plot of what the actual L thing was from the optimization part. So remember in the optimization thing, the thing I started the lecture with, we had this purple curve exactly, right? And I asked, and that was like this L hat, this estimated loss. And we asked, how good of an estimate is this thing of the true expected loss? And this is what the curve really looks like. And so here we see the kind of the trade-off we talked about above. So P describes kind of like the complexity of our function class. If we increase P, recall that this is entirely related to, like, this is related to this function class FP. So increase P, the number of polynomials like the degree of polynomials is bigger. So what do we see? What we see is clearly as P gets larger, then this line gets farther and farther apart. Okay? P is small, it's pretty reasonable. Like the estimate's not that far off. You increase P, this estimate gets further and further. Okay, this is describing exactly this relationship. That these two, their difference, gets larger and larger as F gets more complex. Okay, very, very important. And the other thing is that if you increase N, they will get closer and closer. So what that means is if I were to increase N, you would see something like, I guess I'll erase this, but you'll see that this line now becomes very similar, but now maybe the peak would be like over here. So they get closer and closer until eventually the P at which they start splitting apart gets larger. Okay, I'll erase that because I have some better plots about this in a second. So to like really reflect that point on the data part, I can plot not just the degree of the polynomial or the complexity of the function class. So, right, so like this plot was really talking about increasing the complexity of the function class. I can now plot n on the x-axis instead of the complexity. And that's what the second plot is, which is if I increase n, what I'll find is that at the beginning, there's a big difference between these two. And as it goes on, this difference gets smaller. And here, instead of here I'm talking about how n scales, so what I had to do is I fixed a polynomial degree 4. Okay, so that would be looking at exactly this situation here. Right? So here there's a fixed n. So maybe I should say that is so below I fixed p, here I'm gonna, in this guy, there's clearly a fixed n. And maybe fixed n to 100. So that would be around here. And here we fixed p. Sorry, p equals to 4, which would be this point here. And we can see that, yeah, so as you increase data, these two guys get closer and closer. Okay, these are the two relationships that we basically get between these two guys. Okay, so what does this kind of tell us? What this tells us is that right, at the end of the day, we need to somehow pick our algorithm. What is the algorithm we're going to use? What is our learner? And for that, we need to pick a function class, which it's searching over. So what function class should I pick? We have all these polynomial degrees, and I was saying which p should we pick? This tells us that we should pick p somewhere around here. Because here we get a nice trade-off. What happened there? Here we get some nice trade-off where we can minimize this better and better because the p is getting bigger. But here there's some nice middle ground of the estimation error is still not too bad. But then you find that if you make p too large, then your estimated loss goes down, but then your estimation between the difference between them is just getting larger and larger. So at this point, you find that the true expected loss of our predictor is really the smallest. So that so this is the p we'd want to pick, something like 4 in this case. Okay, but but how do you do this in practice? You don't know what this is. You don't know what the expected loss L is, right? All you know is this guy, and you don't even know it across all data sets. This is plotting how it looks. You only know it for a specific fixed data set. And so we're going to cover that in maybe 3-4 slides down. Okay, but before covering that, I'm going to just dive a little bit deeper into what this term is, and kind of how low can we kind of expect this green point to get to? What can we do to make it smaller, and how things in a slightly more precise way than we've talked about. And then I'm going to come back and tell you how in practice, when you implement things, you can actually get something like this. You could actually plot these two things and then make your choice. Okay, so we're going to come back to this question of how in practice you actually get a curve like this, look at that curve and say, okay, I pick p equal to 4 because I look at this stuff, and now I run the algorithm with p equal to 4, and that's the predictor I use, because I can expect it to actually have to actually predict things well. Remember, this is our representation of how well we can predict new data. This tells us that we predict the new data the best when we train with p equal to 4, when our learner uses p equal to 4. So I guess two people online asked, why not pick p as small as possible? And the reason to not pick p as small as possible is because we can see, okay, if p is really small, sure, these two are really close. But at the end of the day, you want to output a predictor for which this expected loss, which once again, we should, the claim here is that, and hopefully we've agreed on this, is that this thing represents how well we predict on new data. And what this would tell us, if we picked really small p, let's say 1, then this thing is large, the expected loss is large, and therefore we predict poorly on new data. Okay, and sometimes, I give you another wording, which is sometimes this expected loss term thing is called the generalization error. And maybe this gives more kind of intuition to the term, which is this tells us how well do we generalize to new data. So p equals small p, you generalize poorly. Poorly in the sense that if you make p larger, you generalize better. But you're trying to understand, really the goal is how do you pick the right p, and you really need to know this curve. So we're going to get to that curve in a second. But before that, we kind of understand where certain errors are coming from in a slightly more precise way than what I just said in words. Yes? Right. So maybe I slightly skipped over this. So the P, as you've seen before, it was the polynomial degree. It just tells you from what function class you chose from. The D, I kind of wrote above here. Did I write it here? Maybe I did too. Okay, I didn't. So I write the subscript D. Where is it? Here, got it. So remember, we can think about the data set as being random or not. And here we're really going to think about the case where our data set is random because we're going to care about how we perform over different data sets. Okay, so we're going to care about this like expected performance over different data sets of our learner. So we're going to treat the data set as random, which means that the learner is now a random variable. And so for like all that really means is that for different data sets, you're going to output a different predictor. And just to make it very explicit, so like really like I could, so I write this thing. Of course, this equals, so I just write this to equal this. And to explicitly denote that I have dependence on the data set, that this thing, if you change D, then the predictor changes, and that D is a random variable here. And the reason I kind of write this is because if I didn't write this, then for instance, imagine I want to take in a new feature, then I have to write this kind of ugly notation, which is here I output a predictor, and then if I take in a new feature, I would then write something like this, which actually makes sense, but it looks very weird because this thing outputs a function, and then that function takes in a corresponding feature input. So to avoid this kind of notation here and later on, I write this to denote the random predictor. Yeah, and this becomes important because when we want to talk about like how does, okay, so here the data that we choose, there's going to be some like random set of points, and then we pick the predictor based on those random set of points. And when we want to talk about this kind of expectations, we need this dependence on the data here. That's really all I want to say about it. But yeah, so going back to this question, the D here is really just pointing out that f hat here is a random variable. And so the f hat is also a random variable. And that's why there's expectations here. You want to talk about how does this expected loss, right? Like so there's this expected loss, but it changes for the different data sets. So if you have a different data set, you get a different predictor. And for each one of those predictors, you can then calculate the expected loss. And you want to know, like, on average across all the data sets, kind of what is my, like, what loss do I expect from my predictor? And this is once again to emphasize the thing that you really don't know what your data set that you're going to get is. In practice, you're going to find that you don't have this, like, you don't actually have this expectation. But in theory, you first study how it does, like, on average across data sets, and in practice, you just have one sample. Kind of like for the coin flips and stuff, you study how you would do, like, on average across all, let's say, like, coin flips, all 5 coin flips, how your estimate would do. And then in practice, you really just get one flip. But yeah. Okay. Maybe that's all I say about that, too. Oh, I have lost network connection to Google Meets. Isn't that interesting? What happened there? Let's try refreshing. Am I still on the call here? Yeah, I guess this guy is fine. But what happened here? Okay, give me 1 second. It seems I've gotten locked out of UWS somehow, so I need to re-log in now. Okay, I think we're in business again. Okay, we had a bit of a hiccup, but it seems I'm still cooking with the iPad and everything's okay. All right, sorry about that. Let us continue. So the story was, before just telling you how we're actually going to get this curve, this true expected loss curve, and make our decision of what P to pick, we talk about how to decompose this into different error terms first. And this is where we kind of were at last time. Okay, and the way we were talking about doing this was that we said, first, let's do a little bit of a study of like what kind of predictors we would pick if we had like extra information by our learner. And then what's going to happen is we're really going to compare the loss to each one of these like different kind of predictors. So we're really going to want to decompose this, which is what we're going to do. But before that, we had the study of what are the different predictors that we can compare to. Okay, and like we'll talk about what comparing means in a second. But there's these three predictors. First, there's this F-Bayes predictor, which is the best possible predictor that we could imagine if we were able to pick the best function, like best possible any function, like doesn't matter, like the function class is unrestricted here. It's any possible function from features to labels that minimizes this true expected loss. Okay, so this is like you have full knowledge of the distribution, so you can actually calculate this, and you don't restrict yourself to search over anything. This is F-Bayes, and depending on what this distribution is, F-Bayes is going to be different. And here I try to, so this is what I drew, and like, okay, this is just one case of what F-Bayes might be. And I try to maybe highlight this in a slightly better way with, let's see if this works. So this is what you'll see also in your next assignment, I guess. But I think these plots will hopefully help things. So here I can actually like change data set sizes and things like this. So first, here's the first plot. Okay, oh, maybe this plot. So here is like a picture of what F-Bayes might look like. And I wanted to emphasize like, what does it mean to minimize the true expected loss, right? So the true expected loss is like really how, like what is the loss if you were to have infinitely many samples from the true distribution over feature label pairs? Of course, I can never really give you what the, like a picture of what the true distribution would kind of look like, but what I can do is I can get a lot of samples, right? And so these blue points are a lot of samples from the true distribution. And then what you should think about F-Bayes as being is fitting like basically the best fit to infinitely many samples from that distribution. And so this is what F-Bayes denotes. It's like on any possible function, so you can pick any sort of function you want that best fits this kind of data here. And so this is what it turns out that F-Bayes is in this case. So you can see even here, if you were to get some like new, let's say like data point, right? You can't predict it perfectly because you could see even for like the value of 1, but like for this, like when x is 1 on the x-axis, you can see there's a variety of different values it can take. And what F-Bayes does is basically takes the one, like the best possible one kind of on average across them. So even this F-Bayes is going to have some sort of error on predicting new things. And this is simply just from the variability in the data. Like that, like if you get a new house, let's say with 3 rooms, you can't expect to perfectly predict its price. You can, there's going to be some variability across all houses with 3 rooms. Okay. So that's, oh no. So that's where this guy was. That was F-Bayes. Then we moved on to this F star guy, which is almost F-Bayes, except now what we've done is we've restricted the function class to something that's not all functions. And so if you, as you change this function class, you're going to get different F stars. In this case, we restricted it to lines. And so the best line that fits the true expected loss looks like the following. Okay, if you increase the function class, you're going to get a better fit. And hopefully this isn't too tedious, but like if I go back to this plot, this is what this next plot shows. So this is for the function class being degree 1, so p equals to 1. But if I just change this degree, you'll find that I can get better and better fits for F star. So here is like, this is degree 3. So F star equal to 3, if you look in the legend. So this is the best degree 3 polynomial fit to the expected loss. It's getting closer and closer to F-Bayes. If I get further and further, I get something like, yeah. So degree 5, pretty good fit now to F-Bayes. So you can see here, increasing the function class allows me to put like the best predictor in that function class gets closer and closer to the true best kind of predictor F-Bayes. So at this point, you should think like, okay, like I should just increase my function class. But then comes the trade-off, which we've kind of already discussed, which is at the end, I have to pick based on data. And what based on data means is I have to pick based on an estimate of the loss. Okay? And if I pick based on an estimate of the loss, you can think of that as minimizing kind of like the loss between a finite amount of samples of data. So here would be like 5 data points. And so then you get this F hat thing. This is what we've been really outputting, or what our learners have really been producing. This is kind of like this thing, which is really you would really like to output F base, but you have these kind of issues, which is that you have to work through data and stuff. And I have one more plot for that, which is following. And here, this allows us to nicely vary a few parameters. Okay, so we have 3 things, right? We have F base, we have F star as before, and now we have this dotted line, which is the thing our learner actually outputs. Okay. And now the learner used data to output this, right? It didn't have the true distribution. So that's what these orange points are. Here, this is the case we're at 10 data points, and it tried to minimize the estimated loss on those 10 data points. You can think about that as best fitting to those 10 data points. Okay. So now what happens? Well, as we saw before, if we increase the degree of the polynomial, what's going to happen is that this green guy, so this degree 4, the F star fits the true F base better, right? But the trade-off for this is that now this F hat is going to be like quite far away from this F star, right? This is because the estimated loss is a worse estimate of the true expected loss when we increase the complexity of the function class. And what that means, okay, so that's what we see. We see this like this F hat guy is quite different from F star. And if like we can change the data set, and this means changing the random seed we use to generate the 10 samples. So if I change the random seed, look at this. So all I did was I got a new 10 different points. That's what just happened. And look at how different my F hat is. Now I get a different 10 points. I get a totally different F hat. I change it again. I get a totally different F hat, and so on. So how do I fix this problem? Well, I can fix this by gathering more data. So if I change n to be, let's say, 100, I get a much better fit. And you can see if I change the data set, I also get something that's more or less like fitting F star, and it's not changing as much. Okay, so there's the thing I want to highlight is these 2 parameters, which is the complexity of the function class. And if you increase that, then F star gets closer to F base. And then there's the data set size, which is if you increase the data set size, then F hat gets closer to F star. Okay. That's all I want to highlight with that. Okay. So hopefully that, yeah, that clarified all these kind of things about that. Yes. Mm-hmm. Yes. Right, so we're going to kind of see this through these error terms, I suppose. But if we go back, the problem is you're outputting F hat, right? And so what increasing your function class does is it allows F star to be closer to F base, but you care about how close is F hat to F base. And so you get these 2 kind of errors. So like you increase the function class, you get that F star is closer to F base. But at the same time, what ends up happening is that F hat now gets further away from F star. So there's this you're going to see exactly these 2 errors. It's like increasing the function class is going to allow, yeah, F star to get closer to F base, but F hat to get further from F star. And you have to balance these two shifts. So yeah, so like, once again, in the small data case, it's much easier to see this. What just happened? I have lost my sliders. We try again. So yeah, in the small data case, like what you'll find is that, why is that there? Okay, yeah, so in the small data case, like n is small, and the degree is small, you'll find that, okay, then this line is still maybe not too totally different from, this F hat isn't too far away from F star, like in the sense that the lines are sort of similar to F star. But if I change the degree a lot, so I make the F star much more complicated, then what you'll find is now F hat, on average, is going to be way further apart from f star. So in this case, look at how far away like f hat is from f star. It's very, very different at some points. And if I change and for a different data set, it would be even more different, and so on. So yeah, so like this is a very different thing. So you're balancing these two things of basically f star getting closer to f base and f hat getting closer to f star. And that's exactly what this decomposition we're going to talk about highlights. Yeah.
So f base has like all of the possible, like the highest number of
yes, like basically p to infinity.
Star is limited by polynomial, and hat is limited by polynomial.
Yes. And it's exactly what we're going to find in essentially these decompositions. Yes, so f hat, the limiting thing is it's limited by the the function class size, which is the polynomials, and the fact that it has to use data instead of the true distribution. Yes. Yes. We're allowing, and actually if you allow all polynomials of up to infinite degree, because of the Taylor approximation, you can basically approximate any exponential or anything. So, but the point is you can allow anything like exponential, literally anything. If you could pick any function in the world, that's what it is. And even then you can see you still can't get perfect prediction because just for for a specific feature, you could imagine once again, 3 rooms, you can imagine there's not just exactly one house price. There's a variable amount of correct house prices kind of. And so f-base does the best it can given that noise in the labels. Okay, so some very quick questions, which was what does the seed do? The seed just changes the random seed we use to sample the data set. So if I change the random seed, that just means I get a totally new data set of whatever the size n was. Yeah, and in the next assignment, you're basically going to play around with implementing a few things to get these plots, and then you can move the sliders around and see things. Okay. So we had this decomposition of the array, and it looked like this. All we did was, this is the thing we care about, right? Which is the expected value of the expected loss of our predictor across different data sets. Okay. And then we do this trickery that's very common actually in kind of a lot of theoretical applied math things, is what you do is you add and subtract. So this is 0, this is 0, terms that you would like to talk about the error between things of. So here I add and subtract L of f star, which is the true expected loss of f star. Okay, so all I've done here is I've just got the same equation, right? There's an equality here. But now, I added something that's 0 and I added something that's 0. But now the beautiful thing about this is you can talk about these terms in a more intuitive way, which is you can think about how much error is there between the expected loss of f hat and f star. How much error is there between these two losses? How much error is there between L of f star and L of f base? And finally, how much error is there? What is the actual true expected loss of the best possible predictor we can imagine? Okay, and we said that this thing, even if these were all 0, you did everything as best as you possibly you had the biggest function class with infinite data, you still get some loss just from the inherent noise that you get from when you fix a feature, there might be a lot of different correct labels in some sense. Okay, so for that reason, this guy gets the name of irreducible error. It is the error you could not reduce even if you had the biggest function class and infinite data. You just couldn't do anything about it. Then there's this other term, which is the approximation error. And in some sense, this is the best possible approximation in your function class to f base. This is the error between these two. Still nothing to do with data. So these two terms have nothing to do with anything about data. All they had to do is this was underlying noisiness of the actual true distribution. This is just because of your function class. And I write it below. And finally, there's this last thing, which is the only place that your data actually causes problems. And this is the difference between the expected loss of f hat and f star. And this term, you're going to find that we've talked about almost exactly what happens to this just a few moments ago. And we'll break that down in a quick second. But first, I tell you what in words, here's what I was saying. The irreducible error, this is due to the inherent noise in the labels. And the way you can improve this, it's called the irreducible error, but if you really wanted to try to reduce this thing, what you'd have to do is you'd have to gather better feature information. So what you'd have to do is you'd have to go out and gather not only maybe the number of rooms information about a house, but you should go gather also like the number of people that live in the house and the square footage and the location and this kind of stuff. You get this new information, and now you can hope to predict houses better, right? So like you can get a better best possible predictor. Because now you can imagine if you had like in the infinite case, if you had all the information about everything, about the speed of the wind and the like, I don't know, the neurons in everyone's brain and everything, you can predict exactly maybe the actual price that people would want to pay for the house. So then you would finally get this irreducible error to 0. But it really requires all the information about everything going on in the world. Okay? So increase feature information, you reduce this. But in practice, no one actually really talks about that, and that's why it's called the irreducible part. It's like you always think you have some fixed information. What can you do with that? Well, at least that's what the machine learning setting cares about. So now there's two other things left, which is approximation error. And I said this is due to the function class just being too small. It really means that f base is not in f, right? You can't represent f base. So how do you make this smaller? So this guy decreases, the approximation error decreases if I make the function class larger, as we saw. Okay, so far, yeah, so we've got, this is a simple fix to that. Okay, and so here's kind of the culprit of all the problems, is this estimation error guy. And this is due to the random data set, right? It's due to the fact that f hat is predicted based on the data set, not based on the true expected loss. We're not minimizing with respect to the true expected loss. And here there's two factors. The first is always the case, which is this guy decreases if you increase n. So if you can always make n as large as possible, there's no downfall of making n as large as possible. This will always just help you. But in reality, you kind of also in some sense assume that n is fixed. You have like some fixed amount of data. But if you could gather more data, that will always help you. So then you're left with this last thing, which is now, here's the problem. Estimation error goes up, it increases, if you increase the function class. Okay, so the estimation error is going to go up, meaning f hat, like its true expected loss is further from the expected loss of f star, this term. So that's going up, but you benefit from the fact that the approximation error goes down if f gets larger. So there is these two battles, okay? And so there turns out to be this nice middle point to picking these two. Okay, so there's like these special cases called when do you have a high estimation error and when do you have high approximation error. So you'll have high estimation error, this guy will be large. When n is small, right? Because the bigger the n is, the smaller this is. And when you have a large function class. Okay, so you have high estimation error, meaning your estimate of the true expected loss of f hat is going to be, it's going to be high if you don't have enough data and you chose a really big function class. While you're going to have high approximation error if two things happen. So first of all, if your function class is simple, right, it's not like large enough, but in particular, it really depends on what f base is. So if f base is too complex for you to model with f, then you have this problem, right? But you could very easily have the case where f base is just, maybe f base turns out to be a line, like it really is the best fit is a line. Well, then having f as just f1 would be good enough. Okay, so there's some relationship here. So the choice of this really depends on how complicated should f base be, or is it for your problem case. Okay, and then I'm going to give you one plot, but before giving the plot, I just want to it might not be obvious why this guy, okay, should get smaller as n increases, and why it should get larger as f increases. Right above, just remember two things. So in this above thing, when we talked about, when we talked about this, we said here, this is the thing we have some knowledge about, which is the expected loss of f hat relative to estimated loss of f hat. However, that is not the terms we see here. So what do we know about here we have the true expected loss of f hat, but here we don't have L hat of f hat. We have L of f star. So how do we relate this? And it turns out you do the same kind of trickery as you did here, essentially, to do this. And I show this because this is a really kind of a classic thing in machine learning theory world, and I think it really highlights exactly why you cared about the difference between estimated loss and expected loss of f hat. Okay, and so to do this, it's another add and subtract business that allows you to relate to terms that you know about, right? So we want to relate to I just pull this up just to make sure I don't make, so anyways. So you have this thing. And so, but remember, we know knowledge about L, like the estimated loss relative to F hat. So we just introduce that by adding and subtracting it. This is the usual trickery to do this. Okay. So this is the first term, right? I just copy and pasted this guy. Well, I wrote it down. And now, what do we want? So I can make it very clear what I do. So I'm going to subtract this, but not quite this. The thing we know we know the relationship of this for L hat. And now I'm going to add it back. So I just add and subtract it. So I just added 0, right? Add and subtract the same thing. Notice how this thing is going to be something that we can very nicely, we already know what's going on with it. I'll come back to that in a second. And now we're going to add and subtract one more thing. Well, okay, so then we have this guy here. And we could just leave it, but we're going to actually add and subtract one more thing. So we'll keep this guy. But the thing we're going to add and subtract is not L of F star. Okay. But we're going to add and subtract L hat of F star. And there will be a reason for this in a second. Okay. So I continue down here. And then we just have this guy from before. Okay, so all I did is added and subtracted two things, which basically give you, like, add and subtracted this, add and subtracted this guy. They're just 0, but they allow us to talk about some new relationships between things. The first thing to notice is that this guy here is always less than 0. Okay, why is that true? Well, oh, there's a missing. Why is there no? There should be L hat here. Why is that true? Well, it's because L hat of F hat of D, right? How was F hat of D chosen? It was chosen to minimize L hat. So this thing is, of course, less than L hat for any F. So this is true for all F in your function class. And just remember, F star is just some function in your function class. Okay, so when we talk, so what have we done? We basically related expected loss to estimated loss. And in estimated loss world, we know F hat is literally the best thing for the estimated loss. It is the minimizer of L hat. So then we have this beautiful relationship, which is like what we've been working with, which is in L hat world, F hat is the best thing. So if I compare this to this, right, then this thing is always smaller than this. And therefore, this value is less than 0. So what I can do is just I can forget about that term and say it's something smaller than 0, so I can just plug in 0 there and have an inequality. And so I end up with this relationship, which is just these two terms. And this is kind of the crucial thing. Okay, so I'm left with these two. And now I have things that I actually can have some understanding of what's going on. And this is like really what's happening when we were doing the ERM thing, right? Which is like, we're picking F hat based on L hat. But what we care about is the expected loss. So there's some error between these two things, right? And then further, the thing you really care about, or like then there's some error between this guy, which is the thing we output and its expected loss, and the true LF star as well. Okay? So this is kind of how you should think about it. And more importantly, this is the thing we've already seen before, right? This thing we've seen before, it was like, what did we, I guess we didn't really call it. But the important thing was that this thing, difference between expected loss and estimated loss, this thing decreases as n increases and increases as f gets larger. Okay, and it's the same story for this guy, but this guy's not as interesting, really. This is just like some fixed thing, and this is a good estimate of this for the most part. So the story boils down to this term here. So all this to say is that the estimation error can really be thought of as the error between the estimated loss and the true expected loss of f hat. And that should in some sense make sense. Like how good f hat is to f star really depends on how good your estimate L hat was to this based on the thing you chose. Okay. Okay, so why did I say that? All that is to give the intuition of this, right? We knew this for this term, which we communicated earlier. And because of that, I was able to argue that the estimation error here had the same exact properties. It was through that. So this is just to basically demystify this claim here. Okay, now we can plot some things. So all I've done first is I just written out what we've already seen, this decomposition of errors. And now I'm going to plot these things. Like I'm going to plot all these guys and see what it looks like. And remember, you should think, and there's one more term, which is this L estimated loss. So this is what the plot looks like. Okay. And you've already seen two of the functions on this plot, which is the purple and the orange one. Right, so the purple one you've seen. This is like the L hat term. This is your estimated loss is getting smaller as the function class gets more and more complex. Okay. This guy is the true expected loss of the predictory output. Is actually it's getting smaller and smaller and smaller, but then it starts getting larger. Okay, and now we can understand why this is kind of happening through these two extra terms here. Which is here's the story. So L f base. It doesn't change with the degree of the polynomial, right? This is the best function, regardless of your function value. It's like literally has choice of all functions. So it's just the fixed best thing you could ever imagine. L, this expected loss of f star of p, right? It's getting smaller and smaller. It's fitting the data better and like the true expected kind of data distribution better and better. As p gets larger, right? That just means the function class gets bigger. So that's exactly what we see here. Right? Okay. So now what's left is to like what actually happens is we don't output f star, what we output is f hat. And so we should compare these two things. Okay. So maybe this guy, this f star, these two, this is the approximation error, right? L of f star relative to L of f base. That's exactly the approximation error. I guess I can write that here. This is like at every point, this is just the approximation error. And then this difference, that's estimation error. Okay, and here's kind of the beautiful thing, is also we definitely don't know what L of f star is, right? But we can kind of we know what this L hat thing is. And we said that this relationship, this estimation error, which is the difference, right, the difference between these two, can be thought of as just the difference between these two. So, roughly speaking, this guy is approximately equal to the estimation error. Okay, so become a very important kind of understanding. And yes, okay, so here's the plot. I give you some more visualization for this, which is so far, what we've done is we've only plotted things as a function of the degree of the polynomials, right? And I wanted to add one more dimension, which is hard to do in why is there no slider again? Which is hard to do when in like a static thing, but in here I can actually vary the number of samples, right? And so here I just want to point out what happens when I increase the data set size, right? So this plot so far, everything's the same color as before and everything, but now I'm going to increase the size of the data set. And what should we see? What we should see is that the estimated loss and the expected loss, the orange and purple curves, get closer and closer. Okay, so that's what I'm going to do. So they get closer, and as I increase n more and more, they get tighter and tighter. They get closer and closer. And so what's happening here is you can see that as n increases, the estimation error is going down. Right? Orange to green is estimation error. And you can think of the orange to purple as really like a good reference point to that. Once again, n small, you're going to get them further apart. And even smaller, you're going to get something quite enormous. Yeah. So there's a very big difference when you don't have enough data. Okay, so this is, okay. So that's what I wanted to emphasize with that story. And there is these two kind of phenomenon that happened that people give terms to. And you'll hear there's a lot of machine learning. And there's this idea of underfitting and overfitting. Okay? And I write out, so underfitting occurs here. This is underfitting. And on this side of the plot, there's overfitting. Okay, and what do they say? Okay, so when does underfitting happen? It happens when you have high approximation error, right? When your function class is very small, so high approximation error, where is that? Approximation error is this F star business relative to, so this guy. But you have low estimation error. Okay, so your function, like your estimates are good of the things, so you actually do, your optimization is really optimizing something close to the expected loss, but turns out that your function class is just terrible. It's just like really can't capture anything. So you have like, yeah, so approximation error. So you're kind of like underfitting to things because you're not using a powerful enough function class. And then there's this other case of overfitting, and overfitting is now when you have low approximation error, right? I mean, you have a very complicated function class. So you've basically overfit because you have this very complicated function that fits the data, but you have a high estimation error now. Since your function class is very large, your estimate of the loss is now quite bad. So these are the two cases, and you see that through this difference being the high estimation error, and this guy being the low approximation error. That is kind of the big story. This plot is very important to understand, I guess. Okay, so that's underfitting. Your function class is too simple compared to the data set size. And overfitting is the function class is too complicated. Okay. And this is just the plot you would see if you plot it against data now. So in the interactive thing, I had a slider that changes data set size. Here I fixed P, and I'm plotting as a function of data set size. So what you find is that the estimated loss gets closer to the true expected loss. And in particular, they're both like this F hat is getting closer and closer to F star. Okay, so as data increases, the estimate of this predictor you output is getting closer and closer to F star. I love F star. Right? Why is that the case? It's because like you're optimizing over the same function class as F star is optimizing over. Right? They both have the same function class. The only reason you have a difference is because you're using data. How do you fix that problem? You increase the amount of data. That's why these get closer. Okay. Now we finally get into the real world in practice, like how, like we've understood all this stuff. Oh, okay, what did we really get out of all this? What we really got out of all this is at the end of the day, we still want to pick here. This is what you want to pick. So this is like and what I mean by like, what do you want to pick? It's like you want to run your learner on a function class that has polynomials of degree p. And in general, you like all this polynomial, the reason to introduce all this stuff is like, in the real world, you're picking neural networks and all these other like complicated function classes, and you can have bigger and smaller neural networks, and that's exactly describing what P is saying here. And the question is like, what size neural network should you pick? Well, it's going to depend on exactly these factors. So like, how do you decide on this stuff? And it turns out you can do this empirically by plotting some things. And like, yeah, like what are the things you'd need to plot? The things you need to plot is this. If you plot this orange curve, you're done, right? Like you plot the orange curve, you just pick the point in the middle of the thing and you're good. So to plot that thing, we need L hat, or sorry, we need the expected loss of our predictor. How do we get the expected loss of our predictor? And that's the question. That's this question here. So in practice, like we only have one data set, first of all. And then like, how can we tell if we're overfitting and how can we pick this best point if we can't calculate the expected loss, right? So you might answer like, okay, like I can estimate it, right? And that's kind of what you're going to do. But like, how are you going to estimate it? Like, what we kind of have an estimate of it, right? We have this purple curve. L hat is an estimate of this. But look at this thing. This estimate is like quite bad. Like, clearly this thing is not following the same trend as this. So is there some way to fix this? Like, how can we get this guy? And maybe I take like one or two answers if anyone can think of this. This is like also, I guess, an important point of all of machine learning. Yeah. Right, but that like I want like that might tell you like how confident you are in terms of how close L and L hat are, which is what we already kind of had above in a sense. We said that like I gave you this thing that, oh, L hat relative to L, it gets further apart as the function class gets larger and larger. You can really make that more formal. I just like you would really show that it's bounded by something that scales with these terms, but I didn't want to write out the terms. So like that's we already kind of have that. I just want like I want to be able to plot that thing like somehow. Yeah.
A threshold value and the slope of purple line is below that, so like it's approaching flat. That's those are.
But how do you like? So the idea is something like pick a threshold value, and then once L hat, which is the purple line, gets below it, you decide to stop or something. So like, yeah, like at some point it's going to get below it. Like L hat will eventually, with a large enough p, get to 0. Okay, this is the first claim. So like you will of course get below some threshold. But like, what does that mean? Like imagine you pick your threshold over here. Then you get below it and okay, your true expected loss is over here. You have like no reference for what to pick for the threshold. Oh, you mean like if the slope gets not too right? That actually might be not a terrible idea. Like if it stops decreasing so much, but I'm not actually sure what happens with that idea. Okay, worth thinking about maybe more. But that's not what I was looking for. Is the point? Okay, I give you so it's kind of a funny, easy solution. So let's go back to this story here, which is I said kind of the whole problem with why this estimate was bad was because we gathered data and then we picked based on the data. Well, here's an idea. After we've gathered our data and we've picked f hat based on the data, right? Now f hat is we've picked an f hat, right? So now we have a fixed f hat. So guess what? You can now go back to this case, which is now we've picked an f, and now guess what? We're going to gather new data. Okay, so we're going to gather more data. So we have an f hat, and now I'm going to go and I'm going to gather some more data. Let's go gather some more house information, whatever. And then I'm just going to test my f hat, my predictor on the new data. Right? This new data had nothing to do with how I chose the f hat. So I can think of it as having two data sets now. I have a data set to start with, which is how I pick my f hat. And then I'm going to gather new data and evaluate f hat on that. And why would I do that? It's because now, if I evaluate f hat on that, it'll look like this, which is now I'll have my like this f hat. Now I'll gather new data, and you don't have any of these problems. Like the expected value on the new data of L hat is like of L hat of f hat is good, and so on. So this is the idea: is that yes, you pick f hat based on your data, and it has this problem where it's going to overfit the data and so on. But if you want to get an idea of how it performs on new data, why don't you just get new data? You get new data, you test that. Okay. So guess what? This is the famous words you've probably heard in machine learning before if you've looked into it much, which is called having a training set, the data you train on, and a testing set, which is the data you're going to test on. Should make a lot of sense. You're evaluating your model on the testing set, you're training on the train set, but you have, like everything we've discussed so far has always called the data set the training data set. And so you always fit to this training data and so on. Okay, so yeah, this is kind of an important thing for implement. Like this really ties the whole picture together, and that's going to give us an estimate of this that's actually going to look pretty similar to the above plot. So here's the solution. Estimate this L f hat of D business with a different data set. And we will call this data set D test. This is the standard. Okay, but there's just one little caveat, which is like in machine learning, you usually don't get like you're given a data set and you can't go get more data. Okay, so you simulate this by kind of restricting yourself on what part of the data you use to train. Okay, so like there's really no difference of having a giant data set or having a data set, using some of it to train, and then saying you didn't touch the other half, and then using that as your test set. That is no difference than saying, oh, I went to gather it. Like there's no, basically the important thing about the test data set is that you didn't use, like your predictor wasn't chosen based on it. Okay, so this going to gather new data is just as easily simulated with saying, I use data that I just didn't use to like output my predictor. Okay. So that's what's gonna happen. So since we can't gather new data, we split D into D train, comma D test. Okay, this is called like your training test split. So you're gonna train whatever. You split into these two parts, and they look like this, which is now D train. Will look exactly as before, okay, except now, like as before, I mean as your like the data sets we've seen, except now instead of going to index n, right, we're gonna have to like stop early. We can't use all of it. So we're gonna go to index n minus m. And m is now going to be the size of our test set. Okay, so this is our training data set. Now we have a testing data set. And the testing one is just of size m, and it's the last m points. Okay. So and now this guy actually goes up to the end, xn. Okay, this is a pretty important thing. Yeah. So how many points do you have in dtrain? The way you say how many points, do you say what's the cardinality of my set? Like how many things do I have in there? So this thing is n minus m. So now instead of having a training data set of size n, we've always used size n to do everything. We now have n minus m points. And now the test data set is of size m. Okay, very important. Okay, so we did all this. And then, yeah, okay. Then, yeah, I'm not even gonna write it. Then do everything as before with wherever you saw D, just use D train. Okay, so like D train is now the previous D we've always seen. Pass that into your learner, output the predictor, whatever. F hat is now based on D train and so on. Okay, what do we do? Let's look at how but what do we do with D test? What we do with D test is now to estimate this expected loss of the learner we actually, or sorry, the predictor we actually output. So how would this look like? What this looks like is this L hat. Okay, so let me show. So this is a little bit wrong. Why is it wrong? Because what I meant to emphasize is that now we train the learner on D train, which means that this thing here, the estimated loss, is now based on D train. And maybe just to emphasize, I write here, and I hope you understand that this is using the training data points, right? Okay. So that's what's changed. F hat is now based on just the training data set. Plot for L hat is the same, as you might expect. However, now what we have is actually a good estimate of L of F hat, because we use new data to estimate it. So it's no longer has this, what is called this, doesn't have a bias towards, like, doesn't have this, yeah, this big difference here. It's not the fact that as the function class increases, there's a difference. So this L hat is really quite close to L. Okay, so said one more time. If you use L hat based on the test data set, that is a much better estimate of L of F hat, the true expected loss of your predictor, than this thing was, which is L hat on the training data set. Okay, so now we've gotten to the two curves we really wanted, right? Which is now we have the thing we actually optimize when we train and whatever. And then we have something that really estimates the like, once again, the thing you should hopefully believe is that this thing tells you how well you predict on new data. And now we have an estimate of how well do I predict on new data. So if I want to pick, right, like if I want to pick what polynomial, like what's the complexity of the function class I use or whatnot, what am I going to do? I'm going to pick the one that gives me the best predictor that predicts things on new data. That is going to be over here. So this would be the one I choose. This is going to be the polynomial degree I choose. Okay, of course, what happens here? What happens here is that this requires me to actually like train, and this is what happens. You train multiple learners on different sizes of function classes, right? So I train with polynomials of degree 1. That's one, like I solved that. Then I train with the other one, then so on. And all of them produce different predictors, right? Then I test all those predictors, or like, yeah, I evaluate them on the test set. And then I say, okay, the one outputted by the learner that used degree 4 polynomial functions, that's the one I'm going to use, right? Because I have a variety of ones to pick from. That's exactly what this plot tells me. And I'm just asking which one do I pick? Like which one learned the best, kind of like. And so yeah, this is what tells you which one to pick. Okay, so that is what really happens in machine learning, and I'm going to cover one more. So people like instead of using this like saying you change your function class, it's going to turn out that we have this other parameter that kind of does this in a slightly nicer way. But this idea of changing, like searching through this is called this like, in some way like hyperparameter tuning and stuff. It allows you to like search over different learners, and then you pick the one that gives you the best kind of predictor. Yeah. So like all you really need to do is plot this and pick this. The only reason I plotted this thing is to show you that like, okay, L train is going down and there's this relationship. That's it. But like at the end of the day, you really just need to plot this thing and just pick the best, because this is all you care about. So you just plot this thing, pick this, and you're good to go. But okay, what this will tell you is like, yeah, like, I don't know, it just gives you an idea of how far away your estimation is. Like if I increase data, what will happen, and so on. So it just helps you see this relationship, really. Yeah. Go ahead.
Finding like the minimum value of like our test that we define like what our learner function that we make
the question's kind of like, what's the order of operation of defining learn and stuff? Well, so the order of operation is you just have multiple learners, right? So there's a learner that learns with polynomials of degree 1. Then there's a learner that learns with polynomials of degree 2 and 3 and 4. You run all the learners, right? And from each of them, you're going to get a predictor. And now you maybe have like some meta algorithm in some sense, which is the one that just picks the best predictor from all the learners, right? So it's like you have different, I don't know, here would be like you have 7 different learners. Each of them produces a predictor, then just pick the best one. Yeah, the question is like, what should you choose from the training or the test? So you always pick based on the test curve. Like the training, so all that this training thing is, yeah, like it's just telling you that as you increase P, it's going to go down. But that's as like, this is just telling you how you're doing on the trained set. But that's nothing, well, it might or might not be reflective of how you do on new data. And you care about how you do on new data. So this is the thing you care about, the test. Yeah, you should really think about like, in some sense, this is like a test bed or some sense of how you're going to do in the real world, right? Because that thing is like unseen data you've never seen, right? And then you run it on that and see how you do on it. And that gives you an idea. And what you want to pick the predictor that gives you the lowest of this. Okay, that's all I have to say about that. And we can get started on this. And then we will continue with this. And I maybe very quickly see anything. Okay, maybe it's too, I can't really read all these things, but like maybe the one thing I wanted to mention about this stuff is there's just a kind of maybe a question of like, how do you pick M? And usually M is like, it varies, but maybe it's something like 10% of your data gets chosen for testing or something like this. So like if you have 1,000,000 data points, maybe you use 100,000 to test, or like you want to use as little as possible actually, because like the more you can have for training, the better your predictor is going to be, but then the worse your kind of estimate is going to be on choosing at the end. So yeah. So there's some like, I mean, it's really just like once again, it's a thing you tune. You choose like you kind of just choose it and then hope it's a good choice. It's not too systematic. It's not really too systematic in practical world. Okay, so now I tell you about this other thing called the bias variance trade-off, and this is actually like the maybe more typical way that this is introduced, but it turns out to be very related to what I said, and I hope you'll see why I chose to do it the first way and this way, but you'll know both ways as well. So, and what I mean is here there's this things called bias and variance. I introduce you to approximation and estimation error. Yeah, okay. So to get this bias variance trade-off, you have to make some, first of all, some extra assumptions, which is first of all, you have to have L as the squared loss. So you have to assume your loss function is the squared loss. In the previous cases, we didn't make any assumptions about the loss functions. It was for regression, like it didn't even need to just be for regression. We'll see that for classification, the stuff we said above also holds. But for this bias variance stuff, we really do need L to be this squared loss, okay? And then we can decompose the error in a sort of similar way, but we get some slightly different terms that we relate things to. So the first step is like identical, and I exaggerate the similarity by literally taking this guy, copying it. So you start with this, and then you add and subtract something, and you add and subtract the thing we've already seen. So F base. Okay, and now instead of adding and subtracting L of F star, right, there is something else you kind of do, and I don't want to get into all the details, but essentially okay, I'll tell you the high level story, and then I write out the terms, and then maybe we end there. So if you expand this guy out, this is why I've assumed squared loss. You're going to have this thing, which is like this like integral over things squared, like the loss thing squared. And then within that squared thing, and maybe I'll go over this in a tutorial or in the course notes, but you don't need to know it, like all the details. You can then inside there add and subtract something that looks like F star. And if you expand and simplify, you're going to get something that has 3 error terms like before, but they're not called approximation and estimation error. They're something different. And I write them out, and then we talk more about them next class. Okay, so the first one is what is called like the variance kind of term, and it looks like the estimation. It doesn't look like it, but it gives you the same kind of information in some sense. Okay, and this is the expected value of the conditional variance of your actual predictor. And I'm going to write some things. Okay, so this thing in here is the variance of f hat conditioned on some feature x. And I guess here I should really like this. That's your variance. There's a bias term, and I'll explain what f hat is, or f bar is in a second. Then there's a bias term, which looks like f bar of x minus, and now here we actually have f base. And these are all random variables x, and this thing's squared. And then there's one more term, which is the original L f base. Okay, and I'll make this cleaner next time, I suppose, but this is what is called the variance, and this is what is called, this thing inside here, is what is called the bias. And you're going to have that this thing is approximately equal to the estimation error, this thing's approximately equal to the approximation error, and everything basically holds as we've seen before, except now you don't have to talk of like, yeah, we talked about some nice things like f star and stuff. Here there's this f bar, and I think it's much more confusing to talk about, but we'll still talk about it, and I'll show you what it kind of is. And there's this relationship, but everything we saw is the same story, and you still talk about the test set and the train set and plot their estimated errors and compare those to choose and everything. It's just the interpretation of how the error breaks down. Okay, So I'll get more into those next class, I guess. But this is where we end. And this bias variance is much more commonly maybe used in empirical and like the day-to-day in machine learning. Okay, I stop recording.